Well, let me thank the organizers of the conference for this opportunity to speak, and also for this chance to redo the presentation, which was lost due to technical difficulties in the original. My subject today is the freedom of the physical world. I'll briefly state the classical mechanical picture, and then I'll talk about quantum mechanics and some recent experiments, and we'll do an experiment here. I think determinism, lack of freedom, is the hard edge of physicalism which is being revived with that hard edge these days, particularly by writers like Sam Harris, Richard Dawkins, and Sean Carroll. I think we still underappreciate how radically quantum mechanics changed our understanding of the character of the physical law. The loophole-free Bell tests of 2015, which I'll describe, were a very big deal, and I hope to convince you of that. I also want to leave you suspicious of those who insist that quantum mechanics cannot possibly be relevant to biology and brains. On the classical account, the set of values of the properties of all particles and fields in the world constitutes the current state of the physical world. The physical law is expressed as a set of equations, usually differential equations, for the values of the properties of all the particles and fields. Therefore, given the current state of the physical world and the physical law, we can calculate, at least in principle, everything about the future state of the physical world. But quantum mechanics is quite different. On the quantum account, the properties of particles and fields do not, in general, have values. The state of the physical system is described not by a set of property values, but by an abstract mathematical object called a state vector. It's complex in the mathematical sense that it has real and imaginary parts. The time evolution of the state vector is deterministically governed by an equation, the Schrödinger equation, but the state vector determines only the probabilities of outcomes of measurements. The state vector does not determine which one actually occurs when a measurement is made. So quantum particles don't in general have positions or velocities. Now, as we'll discuss, some outcomes do have a probability of 1 or 0, so whether they occur or not can be predicted with certainty. The most essential feature of quantum mechanics is superposition. This represents a potential energy profile as a function of position with two wells. Here's a particle that is in the left well and is described by the state vector phi left. It could also exist in the right well and be described by the state vector phi right. The essential feature of quantum mechanics is that there is another way for the particle to be in the universe called the superposition of phi left and phi right. This state involves the particle not simply being on the left, not simply being on the right, and it's not really in both since it's just one particle, but it retains in a subtle way the possibility of being found either on the left or on the right. It's a unique quantum mechanical way of being that is not found in our everyday experience or in classical mechanics. The state vector, importantly, is a complete description of the particle. The state vector is all there is to know about the particle, all the universe knows about the particle. The ambiguity about the particle's position is not the result of our ignorance, but is rather an essential feature of this different way of being. Now, if the particle is in this superposition state and we measure the position of the particle, we will find it either in the right well or the left well. We can find it on the left well with probability 1/2, or we'll find it on the right well with probability 1/2. Which result will actually happen is not determined by the state vector of the physical world prior to the measurement. It really isn't. And we now know that with certainty. This way of the particle being in the world has both potential outcomes. There is no previous fact of the matter about the particle's position that determines the outcome. And this is now an experimentally verified statement. I'll talk about how that could be later. First, we're going to do an experiment just like that right now. This is Foghorn Leghorn. He's a chicken. This is Yosemite Sam, a cowboy. I can pick one, decide who to display next, and you might or might not know which one I'm going to pick. If I press this button, the computer chooses which one to pick. It uses a pseudo-random number generator, so it's a complicated program that runs on my laptop here, and it's, as a practical matter, impossible to predict which one will occur. But in principle, I mean, the laptop is a bunch of transistors, so if we looked at the physical world here with the laptop and in fact everything in the room, the state of all the transistors is well defined. And if I knew all that, in principle, I could figure out which one was going to happen next. I'd know what the algorithm was. I'd know which character would appear. If I press here, something different happens. Now, when I press that button, it consults this little quantum box, which is it produces a quantum experiment. It sets up a particle in a superposition state of being in the left and the right well, and then it makes a measurement. And it communicates the result of the measurement through the USB cable to the laptop. So the difference is not easy to see, but it's the case that just before I press the button, if you knew everything there is to know about the laptop, the USB cord, the box, and the state of every physical particle in the room, or indeed the universe, you could not, in principle, figure out, predict who was going to appear next, whether it was Foghorn or Yosemite. So we've just seen an essential feature of quantum mechanics. We prepared the system in a superposition state, and the physical law did not determine what would happen when I pressed the button. When I pressed the button, we forced the physical world to make a choice. In this case, we forced it to make a choice between showing a picture of a foghorn, a chicken, or Yosemite, a cowboy. The physical law did not constrain the physical world into making one or the other choice. Now, please note, I'm not here talking about consciousness or mind or anthropomorphizing electrons or photons. More than one outcome is possible under the physical law. That's what I mean by freedom. Exactly one thing actually occurred, and that's what I mean by choice. And this is not a special or exotic case. This sort of thing in the physical world happens all the time. Of course, there is a problem, the measurement problem. But let's state the measurement problem precisely. We created this quantum mechanical system that results in equal probabilities of being found in the left or the right well. We have some detectors that can measure which well is occupied. They're embedded in some electronics, all of which is inside the little quantum box. The box is connected to my laptop running a program. The laptop is connected to a projector. The projector puts up an image on the screen, and we all see the image on the screen. Might be a slight overstating of the audience here. The problem is, at what point in that chain is the physical world required to choose an outcome? At what point did the superposition vanish and a specific result appear? We know that the transcript of the history of the universe has one result, say Yosemite on the screen with us watching Yosemite. It does not have a superposition of Yosemite on the screen with us watching Yosemite and Foghorn on the screen with us watching Foghorn. Somewhere in that chain, the choice was made and, so to speak, written onto the transcript of history as to what actually happened. More than one thing was possible, according to the laws of physics, but exactly one thing happened. The measurement problem is to understand where in that chain of events, where was the fork in the road? So we might find an answer, but we don't have one right now. We've talked already about probability and how quantum mechanics provides probabilities. Let's say a little bit more about this concept. Probabilities are the quantification of partial knowledge or incomplete information, following here Laplace or Jaynes. In common classical cases, the knowledge is partial because, as a practical matter, we only have limited information. We don't know where all the particles in the room are, for example. But in quantum mechanics, probabilities occur not just because of practical limitation, but for the fundamental reason that the physical law only yields partial knowledge about the future. Suppose quantum mechanics gives us P1 and P2, the probabilities for two mutually exclusive events, 1 and 2. If P1 is 1, then the event 1 will certainly occur. If P1 is 0.8 and P2 is 0.2, then either event 1 or event 2 may occur without violating the laws of physics. In this case, the physical law provides some information about the future and some degree of constraint, but there is still some freedom for different things to occur. We can quantify the amount of information, measured in bits, that the physical law provides about the future event using the Shannon information measure. In the case of P1 or P2 being 1, the physical law provides 1 bit of information, certainty. In the case where P1 is 0.8, the physical law provides only about 0.28 bits of information, a tendency. If both P1 and P2 are a half, it provides no information about what will happen. The future event is in that sense completely unconstrained by the physical law. The physical law, quantum mechanics, yields probabilities which represent partial information about the future and provides some constraints to future events. The physical law constrains but does not completely constrain the future. Now let's turn to the question addressed definitively by the recent Bell experiments. The question is, might there not be hidden variables that in fact do determine the outcome of a measurement like this? Must there not be a fact of the matter about where the particle is that will determine the outcome of the measurement? Maybe you don't know what the position is. Maybe for some reason you can't know what it is, but how do you know that the information is not there? You could ask it this way. How can you know that a future improvement on quantum mechanics won't allow you to discover that there's really a position there before you measure it? This view is called realism, which is a little unfortunate, but it's called realism, and it's surprising that it's open to experimental test. We can resolve this question by actually doing experiments. I'll quote Anton Zeilinger's definition of realism. All measurement outcomes are determined by pre-existing properties of particles independent of the measurement. The local in local realism just means we cannot violate the requirements of special relativity. No faster than light communication, that's a given. So realism, local realism, determinism, and hidden variables all express the same idea. What happens next is determined by the state of things now. John Bell addressed this argument in 1964 with an amazing result. He considered a superposition state of two particles. They're superposed together, so they'd once been close and are now separated. They're called entangled. They're now far from each other. And he considered measurements conducted independently on each system, system 1, system 2. The measurements are usually done by Bob and Alice. He assumed that there's a fact of the matter for the property of each system before any measurement is made. So it's important, the logic of it. Assume there's a fact of the matter, and he examined correlations between the measurements at 1 and 2 across many repeated trials. The correlations are mathematical functions you can evaluate. Valerio Scariani yesterday, or at a separate talk in this conference that you can look at, defined the CH-SH correlation function that I'll be using. So I'm relying on his description of that function. That gives an inequality, one of the Bell inequalities, that must hold on very broad grounds, just counting possibilities. The Bell result has the power it has for two reasons. First, because it is a proof by contradiction. Assume there is a fact of the matter, quantities have values before they're measured, and derive a mathematical expression that follows from that. Second, because it just involves counting, not any physical theory. Again, I refer you to Scariani's talk for a derivation from counting of the Bell inequality. Here are the details on one of the Bell experiments. I won't go into all the details. You can see Bob and Alice. There's a source, and there are entangled photons heading off to both Bob and Alice. They measure the polarization of the photons, and they can change their measurement apparatus to be at different angles with each other. The correlation function S, according to the Bell inequality, must be less than or equal to 2. This shows a 2007 test by the Zeilinger group. This correlation function S is a function of that angle, which is varied here, and I won't go into the details of that. The key point is that on the assumption of local realism, S should be less than or equal to 2, and you can see that the data points go significantly above the green S equals 2 line, that dashed line there. So every data that's above the green dashed line is a violation of the Bell inequality. You can also see that the quantum mechanical prediction, the solid blue line, is actually quite good. So these are two separate conclusions to be drawn. The first, the experiments clearly show that the Bell inequality is violated, many measurements above the line. So the results contradict local realism. They contradict determinism, that there's a fact of the matter prior to the measurement being made. Secondarily, quantum mechanics does a rather good job of explaining the data. The blue line fits pretty well. There might be a successor theory to quantum mechanics. There are definitely things we still have to learn. But whatever theory that is, it would have to match this data. And it would therefore defy the notion that there's a fact of the matter that determines the outcome before you force nature to make a choice. Since the 1980s, there have been many experimental tests, usually using entangled photons, which have confirmed quantum mechanics and violated Bell's inequality. These have improved on each other, one, by closing one or another so-called loopholes. But until 2015, no experimental test closed all the loopholes at the same time. We had no loophole-free Bell test. Then in 2015, 3 appeared. This one by Hansen's group in Delft used electrons and photons and reported a value of S of 2.42, significantly greater than 2. This one led by the NIST group, strong loophole-free test of local realism. The abstract starts, we present a loophole-free violation of local realism using entangled photon pairs. There's a statistical confidence of better than 1 part in a million. And it ends with the sentence, we therefore reject the hypothesis that local realism governs our experiment. And this one led by Zeilinger's group in Vienna. It begins, local realism is the worldview in which physical properties of objects exist independently of measurements and where physical influence cannot travel faster than the speed of light. And it ends with, the purely statistical probability of our result to occur under local realism does not exceed 3.74 times 10 to the minus 31. That's a very high degree of confidence. So realism, determinism, has been shown to experimentally to be false. This result is independent of any particular physical theory. It doesn't depend on quantum mechanics. If there's a successor theory to quantum mechanics, it would have to have this feature. There is no hidden determinism. The Bell's result and the final closing of these loopholes experimentally is, I would argue, the most profound result in physics since Newton. Now, some would say this has no consequence in, for example, biology. Quantum effects, they say, are a very small thing. Quantum effects are subtle, and real systems decohere quickly, so the world that matters is still classical. Well, let's look at some other recent experiments. How do you tell if superposition is happening? Well, a common way we can see superposition is by doing an interference experiment. Imagine we have a system that comes in here from the left and is put into this superposition state where it has probability a half of being on top and a half of being on the bottom. So at that moment, it's like being in our double well. If the particle is now allowed to move out and be projected onto a screen, which will show its presence, we'll see an interference pattern, as shown by the red line on the right. Here is some detail about rather substantial molecular systems with complex internal degrees of freedom showing precisely such quantum interference. They're at a temperature between 500 and 1000 Kelvin. This is a Talbot-Lau interferometry. It's in the near field. The slits are 100 nanometers wide with a 260 nanometer period. This is a size comparison. The molecule on the left here that was used in that experiment, it's 6 nanometers wide and has been observed to produce interference patterns. This molecule is larger than insulin and comparable in size to the protein cytochrome C on the right. And they, so to speak, go through more than one slit. That is, they reveal themselves to be in a delocalized quantum superposition state at least 250 nanometers wide. Remember, the slit widths are 100 nanometers, and it's a 250 nanometer period. On the question of the alleged fragility of quantum effects, the decoherence program of Zurek has been very helpful. This shows a particular target system, the 2 colored dots in the middle surrounded by an environment composed of randomly placed other double dots. Here the target system is initially in a coherent quantum superposition state, and we simply let time evolve. If we describe just the target, we find it losing quantum phase information and becoming, you might say, classical. The usual way to see it decohering is to watch the von Neumann entropy of the state, here shown as the blue line plotted on the right. As the von Neumann entropy goes from 0 to 1 bit, the state can be said to become decoherent due to interacting with the environment. But here's the thing, the loss of quantum coherence is just due to describing the target system alone. The global system is evolving perfectly coherently following the Schrödinger equation. Decoherence is, simply is, entanglement with the environment. Quantum mechanics doesn't cease to work. In fact, what is happening is simply that the central system is quantum entangling with each environmental system, and they each with each other. The global system is still quantum all the way, and it has the attendant freedom. What about brains? Well, I don't know how brains work. A computer like my laptop here obeys quantum mechanics, but has had all its freedom carefully engineered out. Nobody wants Windows making its own choices. The little quantum box has not. In fact, it has been engineered precisely to capture the quantum indeterminacy. So the question is, have the mechanisms that created the human brain engineered out all indeterminacy? That's fundamentally a question for scientific research. Remember, though, that we've seen that molecules of this size, on the left, have been shown to be in delocalized quantum superposition states over 250 nanometers at 1,000 Kelvin. This is a scale image of a neural synapse. The scale bar on the lower left is 20 nanometers. So if these 6 nanometer molecules, more than 10,000 Daltons, have been observed in delocalized quantum states over 250 nanometers, there's no reason to suppose quantum mechanics plays no role here. Previous arguments about it being too hot and wet to support quantum mechanics are simply wrong. Hot and wet have nothing to do with it. Quantum mechanics works with hot and wet. Of course, you will not see single particle interference effects. That was never the point. The point is there are many, many possible futures allowed by the physical law. This is just a complex quantum system comprised of many parts. It's very far from equilibrium with a lot of energy flowing around. None of that breaks quantum mechanics. In fact, we know this about large quantum systems with many degrees of freedom, far from equilibrium. Quantum probability spreads out. This is a system of 1,000 states with high connectivity. Each one has 10 neighbors, and it starts in a very localized state. The probability density is shown by the diameter of each of the dots. It's renormalized at each time step so that you can see it. The spread of possibilities is a manifestation of the second law of thermodynamics. The entropy, appropriately defined, increases. And that means that the physical law constrains the system less and less. The information about the future of the system provided by the physical law is less as time goes on. Read that more freedom. The world described by quantum mechanics twinkles with possibilities. In classical mechanics, the physical law completely constrains any physical system, including us. Some misinterpret quantum mechanics so that it simply adds a classical random element to the physical law. Now you're controlled by the roll of the dice. This is wrong. The dice picture is a classical picture. We must take quantum mechanics more seriously. In quantum mechanics, the physical law only partially constrains the physical world. We cannot fly around the room, but we have every reason to suppose that our sense of personal freedom is grounded in the character of the physical law. The character of the physical law is that it allows some freedom. The physical law constrains, but does not completely constrain, the future. So to summarize, the history of the universe is not determined by its initial condition and the physical law. The future is not contained in the present. The information about the future is not here now. The physical world is not, in that sense, causally closed. The present does not simply cause the future. Not everything had to happen the way it did happen. The unfolding of the universe is not computable. It cannot be captured by an algorithm. So finally, let me say, the character of the physical law is different than we had supposed for a long time. It constrains but does not completely constrain physical systems. We have learned that the world God has made supports both order and freedom. It has freedom, yet it is not just chaos. It has order, but it is not just machinery in motion. We shouldn't let ourselves be stuck in a mindset inherited from previous centuries. We should not succumb to an outdated, mechanical, deterministic view that's often pressed into the service of naive physicalism. The physical world is just much more interesting than that. And I thank you for your attention.